Um, Good afternoon, everybody, and thank you all for joining. My name is Surya Kamal, and I'm a third year PhD student at the Center for Imaging Science here at RIT, where I work with Professor Rich Hailstone and Professor Nate Cahill. I'm also the regional liaison for the Microscopy Society of America Student Council. On behalf of the Student Council, I would like to heartily welcome Dr. Suyan Hong for joining us today and sharing her research with us. Dr. Hong is a staff scientist in the electron microscopy group at the Center for Functional Nanomaterials at Brookhaven National Lab. Here she uses state-of-the-art TEMs, transmission electron microscopes, to characterize the structure and chemical dynamics of electrode materials during battery operation. Through her research, she aims to improve the performance of batteries. Dr. Hong holds 3 degrees in material science and engineering, a BS from Ajao University, and an MS and a PhD from Korea Advanced Institute of Science and Technology. Finally, I would request Dr. Hong to begin her talk and share her work with us. Dr. Hong.
Thank you very much. Hello, everyone. Thank you very much for your kind introduction, Surya. I'm Suyan Hong from Center for Functional Nanomaterials at Brookhaven National Lab. I do appreciate the opportunity to share my research about phase evolutions of electrode materials for lithium-ion batteries. Before focusing on the science, I'd like to introduce you Brookhaven National Lab, or BNL, and Center for Functional Nanomaterials, or CFN. BNL is located at Upton, New York, and this city has been serving United States over a century. So before the BNL starts the scientific journey, U.S. Army's Camp Upton was here. So you may see this old picture, very old picture where the U.S. Camp Upton. And after that, BNL is currently full of cutting-edge research facilities and talented scientists. For example, the relativistic heavy ion collider, which is RIG, is the first machine in the world capable of colliding heavy ions like gold ions. You can see a big ring over here, where the RIG facility is. Here, physicists from over the world come to here to explore what the universe would be looked like in the first few moments of after its creation, which is Big Bang. BNL also hosts National Synchrotron Light Source 2, which produces very, very bright X-rays. Currently, 29 beamlines are operating, and those provide X-ray scattering, X-ray spectroscopy, and X-ray imaging. And next to NSLS2, CFN is here at Blue Dots. Here is where I'm working at. CFN is one of nanoscale science research center operated by Department of Energy. If you have allocated proposals, CFN is open to users, and all the facilities and staff expertise are available for free. So please take advantage of this opportunity. We are focusing on creating, characterizing, and understanding nanomaterials with various tools. Among them, I'm working with electron microscopes, especially transmission electron microscopes. During this talk, I'll briefly introduce the transmission electron microscope and lithium-ion battery technologies, then discuss with you how I use transmission electron microscope to understand the phase changes of electrode materials for lithium-ion batteries, and summary and outlook will be followed. Electron microscopes are definitely a microscope that allows us to see very tiny details. With our bare eyes, we may see 100 micron big features like our hair. With light microscope, we can see smaller things like bacteria. But with electron microscope, it can discern really, really small things like an atom. So electron microscope offers an exceptional spatial resolution, and currently the world record in highest resolution is 0.39 angstrom, achieved by Cornell University. There are two kinds of electron microscopes we generally use. One is SEM, scanning electron microscope, and the other is TEM, transmission electron microscope. SEM produces the image by scanning the surface of sample with electron probe. So we can see the surface topology. And in TEM, we use the electron beam transmitted through the sample. And so we see a projected image of 3D objects. And here in TEM, electron beam has to pass through the sample. So usually sample has to be very thin, usually less than 100 nanometer thick. When high energy electron beam hits the sample, tons of signals are coming out. And using those signals, we can get images, electron diffraction patterns, and we can do chemical analysis with energy dispersive X-ray spectroscopy like EDX, or electron energy loss spectroscopy and EELS. In general, we use a parallel electron beam in TEM, but we can also make a small electron probe, and we can scan the sample with the probe electron beam. And in this case, we can refer this technique scanning transmission electron microscopy, which is STEM. General TEM instruments offer both STEM and TEM operations. The beauty of STEM is we can do chemical analysis at atomic resolution. Here is an example of silicon oxide, and amorphous silicon layers. And the oxygen KH spectra here were acquired at green circled areas. We can clearly see that oxygen KH is definitely different as silicon oxide. And think about the silicon oxide is only 5 angstrom thick, so it is very powerful technique. And with high angle annular dark field detectors, we can guess the chemical information from images too. From this image, you may see that the edge of tube sample is a bit brighter than the inner area because the surface is composed of an atoms having higher atomic number. We can analyze a sample and nanoscale not only as static conditions, but also dynamic conditions. You may hear about in situ TEM or operando TEM. In situ TEM refers to real-time observation of samples with applying external stimuli like heating, cooling, biasing, or introducing other environment like gas or liquids. Operando experiments additionally measure the material's property, so it ultimately provides understanding in structure, processing, property, performance relationships. I mentioned before that TEM provides 2D projection images of 3D objects, but with tomography, we can learn 3D structures also. We got images with tilting the sample at every 1 or 2 degrees. Then through the computations, we can reconstruct the 3D structures. Here is an example of tripod-shaped palladium lead catalyst materials I got before. Cryo-TEM is an interesting field, especially during the pandemic, because with this technique, coronavirus can be imaged. Cryo-EM is very popular in structural biology, but very people are also interested in this technique because with cryo-EM, we can image the electron beam sensitive materials like lithium metal. In general, liquid nitrogen is used for cool down the sample, but in some cases, liquid helium is also used, which can reach much lower temperature. And this is really good for studying specific physical phenomena at extremely low temperature. CFN has 5 different transmission electron microscopes, and each microscope has its own specialties. Joule 1400 here is good for soft and biomaterials, and Joule 2100F is more versatile to various materials. Talos is the newest microscope installed at CFN, and it has very powerful ADX, so chemical analysis can be done very efficiently. And the large pulpy gap of Talos allows us electron tomography. Excuse me. Hitachi HD 2700C is a dedicated stand with EDX and EELs, and also it is equipped with probe CS corrector, which corrects the errors from electromagnetic lenses. As a result, we can make very small electron probe, and we can improve spatial resolutions in catalysis. Steps also training you without is better. So
Yeah, go ahead.
okay, so cryo-TM is an interesting field, especially during the pandemic, because coronavirus can be imaged through this technique. Cryo-EM is very popular in structural biology, but these days, battery people is also interested in this technique because with this technique, we can image the beam-sensitive materials like lithium metals. In general, liquid nitrogen is used to cool down the sample, but liquid helium is also being used for specific experiments requires very, very low temperatures. CFN has 5 different transmission electron microscopes, and each microscope has its own specialties. Joule 1400 is good for soft and biomaterials, while Joule 2100F is more versatile to various materials. Talos is the newest microscope installed at CFN, and it has very powerful EDX, so we can perform the chemical analysis very efficiently. And also, large pulpy gap of Talos allows us electron tomography. Hitachi HD 2700C is a dedicated stand with EDX and EELs, and also it is equipped with probe CS corrector, means that additional optics corrects the errors from electromagnetic lenses. As a result, we can make much smaller probe beam, so it gives us much better spatial resolution in imaging and chemical analysis. Titanium is very interesting system because this machine allows us to introduce gas around the sample. So we can perform very interesting in situ experiments like carbon nanotube growth or catalysis. CFN also has various in situ holders like cooling, biasing, and heating, gas cell and liquid cells. So, and all the facilities, including microscope and holders, are open to users. And also steps provides training to users. So please take advantage of these opportunities. Using these awesome microscopes, I have been exploring battery materials. Now, it is not easy to live without batteries, especially lithium-ion batteries are being used in many different areas, but still being explored a lot to improve their performances. For example, we want to have a battery with higher capacity that allows us using our phones or tablets much longer. And with comparable performances, the lower cost is always better. And safety is not a thing we can compromise. So to achieve better performance of these, we need to understand how battery works and how the materials inside behave. This video shows nicely how lithium-ion battery works. First, lithium-ion batteries are composed of anode material, cathode material, and separator and electrolytes, and external circuit is connected. When lithium-ion batteries work, it is based on lithium movements between anode and cathodes. Lithium ions are traveling through the electrolyte, while electrons are moved through the external circuits. During charge and discharge, lithium movements are the opposite way. As electrode materials store and release lithium ions, they fundamentally govern the property of lithium-ion batteries. For example, operating voltage is defined by the potential difference between cathode and anodes. And capacity is defined by delta X, which is how many lithium ions are participating in this reaction. And the number of available lithium ions are depending on what is the working mechanism. So commercial batteries are using the materials based on insertion reaction, which is insertion or intercalation reaction. For those materials, they usually have layered structure and lithium ions can be inserted or removed without damaging its original crystal structure. So this mechanism gives a reliable operation, but the capacity is relatively low because limited number of lithium ions are participating. Some materials can store through the alloying, and alloying reaction requires multiple number of lithium ions, so it gives us much higher capacity. However, this mechanism gives us another headache like contact loss or polarization because of the huge volume expansion. Conversion reaction here is also in here, also multiple number of lithium ions are participating, and we can get huge capacity. In this kind of material is usually metallic compounds like metal oxides, sulfides, or fluorides, and by reacting with lithium compounds and metallic nanoparticles are formed. This mechanism still needs a lot of investigation because of voltage hysteresis or capacity fade. My research focuses on how the structure and chemical property of electrode materials have been changed depending on the electrochemical tests or at high temperatures. TEM is a wonderful tool to probe nascent changes of materials at both ex situ and in situ. And my goal is provide the fundamental backgrounds for designing better electrode materials. First, here is an atomic model of cathode materials, which is lithium transition metal oxides. Transition metal can be cobalt, nickel, manganese, or titanium, or sometimes aluminum. As you can see, these materials have very well-defined layered structure, and this structure provides favorable two-dimensional lithium diffusion path like this. However, we cannot use all the lithiums here because too much lithium extraction can damage this layered structure. Then phase transformation to spinel or Russell can happen. Phase transformations bring about negative outcomes like capacity loss and impedance rise. I specifically studied nickel-based cathode material, lithium nickel cobalt aluminum oxide, referred as NCA, because this material is commercially important and Tesla uses this compound as cathode materials in their electric vehicles. NCA provides high energy density and high power density, but safety and stability has been problematic. So I performed electron microscopy work for diagnosing the incipient materials degradation. Before electrochemical test, NCA has layered structure both at bulk and at the surface. This electron diffraction pattern were acquired from the whole particles, and this fast Fourier transformation pattern were acquired at the surface at circled area, showing consistency. And also the oxygen K-edge yields acquired from different areas are comparable, suggesting that crystal structure and electronic structures of NCA are homogeneous before the electrochemical test. To see the changes after charging, which is lithium extraction, different amount of lithium ions were removed from the original material. Half charged means 50% of lithium ions were extracted. Overcharged means 90% of lithium ions were extracted. This image were acquired from half-charged material, and even though only 50% of lithium is used, I can see spinel or Russell phases at the surface, which means locally structured degradation happened. And I got oxygen K-edge yield spectra from multiple particles at each state of charge, and I summarized the data at this plot. And from here, we can see some variations, and these variations becomes much severe at overcharged sample, which means materials degradation happened locally and inhomogeneously. Inside of TM, I heated charged NCA particles to see their thermal stability, as the remaining X means remaining lithium amounts, and as remaining lithium becomes less, material becomes porous much lower temperature, which means oxygen gas is released with phase transformation. Oxygen gas evolution is really bad event because it can react with flammable electrolyte inside of battery, and even in the worst case, if the catastrophic explosion can happen. And at overcharged sample, we see the porosity evolution at 100 degrees C, which is low enough temperature we can reach in summer. Thermal stability is an important factor for battery safety. So this is a commercial batteries, and a researcher in UK recorded the temperature of inside of battery with increasing the temperature outside. And at the first, battery itself can manage the temperature pretty well, but At some point, we can see the hotspots with white colors. And eventually, at some point, this battery under experiences explosion. And from X-ray tomogram before and after breakdown, we can clearly see that internal structure was damaged, hugely damaged. So heat-related safety concerns of batteries are strongly related with thermal runaway. It starts with the composition of surface of anode, then anode materials, electrolyte and separator, then finally cathode materials becomes degraded. The thing is, important thing is, from the thermal degradation of cathode materials, huge heat is generated, and also, as I mentioned before, oxygen gas is released from the cathodes. So thermal stability of cathode materials should be studied very carefully. And even though the thermal decomposition happens very locally, it can affect the neighbors. So localized analysis is very important. From the in situ heating experiment with charged NCA particles shown before, we can imagine that it would be much better to have alternative cathode materials showing better stability. To adjust the properties of lithium transition metal oxides, introducing different kind of transition metal or using different composition of transition metal may work. For example, lithium nickel manganese cobalt oxide, which referred as NMC, can show much better safety feature than an NCA. And in general, nickel gives high capacity and manganese is good for stability and cobalt helps rate capability. To find the good composition of NMC materials, I tried 3 different composition of NMC compounds. In case of 433 composition, it delivers much lower capacity than the others. So I'll exclude this composition for our discussion. NMC622 delivers comparable capacity to NMC811, which is quite good. And I increased the temperature of 2 compounds and get yield spectra at every 50 degrees C to see the thermal stability of these 2 compounds. And these yield spectra are summarized, the graph on the left. In case of NMC811, the features in oxygen KH and transition metal LHs are dramatically changed around 100 degrees C, but these kind of changes were happened at much higher temperature in 622 compositions, which means NMC622 exhibit better thermal stability. This trend is also found in imaging and electron diffraction patterns. Porosity evolutions and phase transformations were observed much higher temperature in case of NMC622 compared to NMC811. So from the systematic in situ heating experiments with different composition of NMC materials, I could suggest that optimizing transition metal compositions can be an effective way to achieve thermal stability and high energy simultaneously. I looked at cathode materials after charge in a coin cell and saw local inhomogeneity. However, this ex situ study may not reflect the real conditions in a battery system because material is already removed from its native environment, like, for example, coin cell. And I also washed the materials to remove any residuals. And also there is time delay between the event and the characterization. So to understand how the materials behave with lithium ions, we need another approaches. An open cell configuration shown here has been successfully mimicked the battery systems inside of transmission electron microscopes. Lithium cobalt oxide is an cathode, and tin oxide nanowires are anode, and ionic liquids serve as electrolyte. And as lithium ions move from lithium cobalt oxide to tin oxide nanowires, we can clearly see how this nanowire is changed with lithium ions. Using this experimental approach, I explored tin sulfide materials. Because this tin sulfide is interesting material as it has layered structure, so lithium ions can be inserted by intercalation. And sulfide compounds are also available for a conversion reaction, which means we can store more lithiums. And the reaction product from conversion, which is tin, metallic tin, can also react with lithium by alloying. It means multiple working mechanisms can store lithium in a single material, and eventually tin sulfide has potential to deliver much higher capacity. So here is a picture of real TM sample folder, and here this is simplified scheme. And the silvery tip here is tungsten tip, and lithium metal was used as a lithium source, and naturally oxidized lithium oxide served as solid electrolyte. And when lithium is inserted into tin sulfide, we clearly see the severe structural changes through electron diffraction patterns. And also from the images, we can see how the reaction proceeds. Lithium ions are introduced from left to the right, and we can see the how reaction proceeds. And from the snapshots of electron diffraction pattern videos, I can clarify 4 steps of lithiation reactions. At first, lithium is inserted into the empty space between sulfur layers, so intercalation happens. Then when further lithium is inserted into this compound, lithium and tin disordering happens. So originally it has layered structure, but it becomes rock salt-like disordered structure. Then with further lithiation, conversion reaction happens. So lithium tin sulfide is converted into lithium sulfide and tin metals. And eventually this tin metal can make alloys with lithium. This experimental data is cross-checked with density functional theory calculations, and our collaborator in Northwestern University identified all the possible phases with different amount of lithium inside of tin sulfide, and they found the most energetically favorable phases, which was consistent with our experimental observation. Battery technologies keep evolving to meet higher requirements of energy, power, and safety. Solid-state batteries which replace the flammable electrolyte with solid electrolyte has been proposed as they are much safer. And these solid-state batteries has potential to provide much higher energy with smaller size and smaller weight. So a lot of huge research effort is being exerted from both academia and industry now. In solid-state batteries, additional factors should be considered. In conventional battery, there is a liquid electrolyte, and liquid electrolyte is very flexible and it is easy to permeable into the electrodes. But in case of solid electrolyte, both electrode and electrolyte are solids and the interface becomes rigid. So other factors like strain can be important in this case. So in this work, strain effect in lithiation reaction was explored with a model system of epitaxial iron oxide thin film deposited on niobium doped strontium titanium oxide substrate. Because of the lattice mismatch at the interface naturally experiences 7.55% of compressive strain here. When lithium ions are inserted into Fe3O4 material, first, spinel structure is changed to Roxel structure based on intercalation. Then conversion reaction follows, and as a result, iron and lithium oxide is formed. When lithium ions are introduced from the top to the thin film, you may see the contrast change in the images, which means something is happening. And after getting this video, I got high resolution TM images to figure out what really happened. And the thin films far from the interface already undergone the conversion reaction, but I found spinel and Roxel phases near the interface, indicating that the strain from the interface delays the lithiation reaction. When the more lithium ions are introduced here, conversion reaction is eventually happened at the interface, and because of additional strain from the volume expansion, the thin film is finally detached from the substrate. From this work, we can learn that strain is an important factor to determine the reaction kinetics. And also, if we control the strain, we can use, it might be beneficial to use the electrode materials undergone huge volume expansions. Electron microscopy is indispensable to understand the materials at nanoscale, atomic scale, nanoscale, and micron scale. But unfortunately, what we are seeing is not always linked to the cell performance, electrochemical performances, because what we are seeing is rather localized. So sometimes it does not represent the general features. So it is better to have another tools like synchrotron X-rays, because it can provide us more average information from the sample. So for example, lithiation mechanisms can be explored at complementary scales. So here I have iron cobalt oxyfluoride nanowires, and inside of TM, we can clearly see how the morphology of nanowire is changed with lithiums. In the meantime, I can make a coin cell with the same material, and I can get X-ray diffraction patterns while testing the batteries. So by combining synchrotron X-ray technique, X-ray-based techniques, and transmission electron microscope, we can obtain more complete story about the phase evolutions in electrode materials based on the electrochemical tests. Multimodal analysis is also powerful to address the problem the battery has. These graphs represent the discharge and charge profiles of nickel oxide, one of conversion time material, and x-axis represents the capacity. As cycle proceeds, the capacity is degrading. And to figure out what happened at nickel oxide, we got nickel KH X-ray absorption spectroscopy, and we find that conversion reaction is not fully reversible, indicating that lithium is not extracted fully. even after charging. So we got high resolution TM images to figure out what really happened inside a nanoscale. And even though lithium is extracted, we found the nickel-nickel oxide phases. And we found that, oh, incomplete lithium reaction, lithium removal is strongly related with these intermediate phases. And this intermediate phase pile up as cycle goes, and eventually we lose the available lithium ions and capacity degrades. Transmission electron microscope provides a wonderful spatial resolution compared to other tools, but the the thing I really want to focus on, highlight is we need to very careful with radiation damage from the electron microscope. Especially the battery materials are fragile under the beam and it can be easily damaged. For example, I have a funny image from NCA particles after stem EOS line scan. You can see these continuous holes were formed by probe beams. So, so for in situ or operand TM work, we look at the same region for a long time. So electron dose has to be managed not to damage the sample. Let me wrap up this talk. A transmission electron microscope is a versatile tool for exploring nanomaterials. I take advantage of this wonderful tool to suggest the regions for unexpected and undesirable events occurring at the electrode materials. In situ capabilities of TM broadens our knowledge in mechanisms of thermal degradation and electrochemical reactions. And complementary studies with TM and synchrotron X-ray techniques enriches our understanding in electrode materials. During this talk, I mostly talk about the in situ TM work, but eventually operand TM, which measures the materials property, will allow us to link the structural evolution of materials with their electrochemical properties directly, and this would be my next goal to achieve. I'd like to thank everyone showing here for their support and wonderful discussion. And also thank you very much for your kind attention. And I'll be happy to take any questions you may have. Hello.
Yeah, Dr. Wang, thank you for the talk. Guys, anyone has questions, we can have a discussion now. Okay, so I have some questions. So when we are talking about capacity, is that the only parameter you are judging the material for holding energy, for like they don't fade out? Is there any other parameter which should be considered?
You mean except the capacity, what kind
Yeah,
of
yeah.
factors be
So the
important?
way, yeah, the way I understood it is like uh, there's one there's only one parameter, the capacity which you are trying to maintain, right? To retain the energy.
Mm-hmm.
And so, is there any other parameter that can be judged on, like
Actually,
performance of lithium ion batteries?
yeah, there are many other factors. So let me find. I feel like I don't have perfect graphs for showing other performances. But for example, here I tested this coin cell at same current density, but sometimes for some applications we want to charge or discharge very fast. So we use very high currents and we see how much capacity is delivered at different current densities. That is rate performance, and that is really important. And how capacity retention is also important. Here, actually, it is not good for capacity retention, but for good materials, this capacity can be reliably delivered for long-term cycling. And also, the operating voltage here is also important. So this is the first discharge graph, and currently we see you see the plateau around 0.6 volt, but this plateau becomes much higher. This is not good. So what is the operating voltage? That is also important factor too. And what else? Yeah, there are many different factors, but yeah, here I just mentioned the capacity, which is very intuitive to everyone.
Okay. And in the earlier slides, you also mentioned there was an image where you were showing the heterogeneous errors, like the material degrading heterogeneously.
Mhm.
So is it correct? Like, do we want a homogeneous degradation? Is that better for performance? Uh,
So in ideal case, degradation is not happening. Degradation is
I
the
know. Yeah.
ideal. But the thing I want to mention here is actually in this experiment, not every particle is damaged. I found some areas are degraded. So what I want to focus is this is very localized event, but still very nascent changes are happening at the first charge. So we need to improve the materials by other methods like surface coating or other methods. This is not not found everywhere.
Yeah. Okay. So what is the resolution you're trying to get here, like for actual in situ real-time observation of materials? Was it
You,
was it 0.1 nanometer or something like that?
actually, for in situ experiments here, you may see that the the scale bar is 50 nanometer, which is quite big, right? So I tried to get high resolution TM images with inserting lithium ions, and sometimes it was successful, but again, electron dose was too high at high resolution imaging conditions. So electron beam can damage the material. So that is one thing I need to consider in next experiments, because in situ experiments in situ experiments, electron beam hits the sample the same region for long time, and materials are decomposed. So I may need to adjust the beam settings or accelerating voltages, but currently what I'm have here is not very high resolution, to be honest.
That's the exact problem I am facing in my research, like
Mm-hmm, mm-hmm,
charging of material. Uh,
mm-hmm.
so I came across a recent research. It's called quantum electron microscope. It is being designed for low dose imaging, but I
Right.
think it's more of a theoretical concept for now.
Mm-hmm.
Yeah.
And low dose imaging requires very good camera too.
Yeah. Yeah. Okay. Anyone else has more comments, suggestions, questions? Okay, so looks like this is it.
Okay.
Okay.
By the way, yeah, you may have some questions or comments about my research or user program at the CFN. So feel free to send me an email if you have anything in mind.
Yeah, that's helpful.
Mhm.
Okay. Okay. So thank you everyone for coming and joining us, and thank you, Dr. Wong, for giving this wonderful talk. I am surely now invested into battery research.
Thank you very much.
Yeah.